Thank you for choosing this track over my good friend's Paul on the other side. I just realized this track, this session, has the longest title, so I'm going to make it a bit shorter. We'll be talking today about full text search. We'll talk mainly about search, then explain what exactly is full text search, and we'll mention Lucene a bit. We'll see how Lucene can be used to perform full text searches. I'm going to discuss other technology. We'll leave that for the rest of the session. And we will also show some neat things we can do with those technologies. Before we start, this is the book that I'm writing right now. That's a shameless plug. This book is one copy of this book is going to be raffled among the attendees here, courtesy of me and Manning, the publisher. So good luck for everyone. That's Raf and Michael going to do the actual raffle. And let's talk about search. So what is search? When I say that I'm talking about search, what comes to mind? So back in the old days, you would have gone to a library full of books, and you knew you were looking for a certain book or a certain topic. You wanted to learn about a topic, and then you would go through all the shelves in the library and go through all the books in every shelf, or you would just go to some index of some sort, whether it's a large book with an index of all the books, or a computer if you are younger. And then you would find the book that you were looking for. Okay, so when we say search, we basically mean information retrieval. We want information, we want to learn about something, and then we go and try to find it using some sort of tools. So in April, like almost a year ago, the internet, the web as we know it today, had its 20th anniversary. That's actually the first website ever. As far as I understood, that's the original URL for that website, as it was 20 years ago. And back then, we didn't have much information on the web. We just had quite a few simple HTML pages, and I don't know what we would have done with them, but basically, we had quite a small place that's called the internet. And things changed, and wrong image, sorry. And we actually had a lot of information put into the internet, and we had to find a way to navigate through that. So it's actually going to find, we needed a tool that would let us find information, this huge place that's called the internet nowadays. And once we had that information, we would actually get a lot of results for a lot of searches. So we actually needed a good way to navigate through the results, right? Not only the results, even if you have a large website, you need some sort of a way to show your users what you have to offer in your website. So that's basically what I'm going to show you today. I'm going to show you how to manage huge amounts of data and allow searches on them, whether it's a search, a basic search, or a full text search. We will see the difference in a bit. And then once you have integrated a full text search engine, I will show you how you can take advantage of what this engine allows you to do and enhance user experience, enhance profit probably, and so on and so forth. So search engines are not only for the web. You can actually take your data, whatever data you have, even if you don't have that amount of data, and use search engines to either search on it or allow users to navigate through it more efficiently. There are actually quite a few other nice use cases, and we'll show them as well. I will talk about the NoSQL bit later. Okay, so before we start, I would want to discuss a bit what is search and how does search work. Since I was a kid, I was really interested in finding out how things work. And what I discovered is whenever I understand how things work, I can find a way to leverage that thing to work the way I want it to. And that's exactly the scenario with search. Search is works exactly like that. So let's imagine I have a bookstore, right? I have an e-commerce web store selling books, for example, or just a library. And for example, I have only 4 books in my store. So each book has a couple of data entities in it, right? I have the actual number of the book. I have its title, right? I have the author name. I have how many pages this book has, and obviously its price. Now, I want to be able to find books depending on some sort of data. For example, I want to be able to find books on a certain price range, or books of certain size measured in pages. So how would I go about that? If as a human, I would just go through all the books probably. I would just scan all the properties of each book until I find the book that I'm interested in, right? But what happens when I have hundreds, thousands, millions of books? What do I do then? I need to somehow make this process more efficient, right? And I have to remember all the time that this is how I work. The computer doesn't have to work the way I work as well. Maybe the computer can do stuff a bit differently. So that's exactly what we did. Computer scientists, I don't know, a couple of dozen years ago, we invented what's called the inverted index. That's basically taking a certain data entity and reversing the process of the way I, as a human being, works. I'm reversing that process to make it work more efficiently for a computer. So if I, as a person, look at a data entity in terms of that document, right? That data entity. In that data entity, I have different fields, right? So the title, for example, of the book is a field, and the author is a field, the price is a field, etc., etc. So that document is split into fields, and then each field has the actual data in it. We call that a term, right? So what we did, we actually reversed it. We reversed the process. Now I'm not looking at a document. I'm going straight to look at the actual terms that I'm looking for, because I know I'm looking for a certain value. So I'm going to look it up on the table, which represents the actual field that I'm looking to find the term in. I will find that term, and I will be able to find, it will reference back the actual document it took it from it. So the process was reversed. Instead of looking at a document field term level, I'm now looking at a term field document level. So that's exactly what happens here. The inverted index represents all the fields that I have, and each field has such table. Each table will list all the terms that it knows about, and each term will reference the actual documents, in my case it's books, and show where that term can be found in which documents. You can see that okay, I have only one, but the Dan Brown term in the field authors, right, it references more than one book, because I have 2 books written by Dan Brown, so I can actually go ahead and find that. So here is an example that I'm looking for a book for all the books with 400 pages. So I will go to the table of pages. In that table, I will scan the table. This process of scanning that table is very cheap, because we use very efficient data structures for that. I will find that term, and I will be able to find right away the actual document. It's much, much better than actually going through all the books to find what I'm looking for. So here's another example. So if I can actually now combine multiple queries, I can ask for pages 400 and author Dan Brown. The first query will match this one here. The second query will match this one here, but I will have no intersection between them. So the query will return empty results. I can either play with the query itself. I can use an OR operator. I can use other value to be able to match more to actually match a book. So far, just a second. Okay. So far, what we've seen is how the inversion process, right? How I can take a lot of data, inverse it to be able to look it up very, very fast and very, very efficiently. And I say again, the actual lookup process, as we will see in just in a few minutes, is very, very efficient. It's not just as you know it from maybe a SQL databases that is table scan is considered very, very slow. Here we use very efficient data structures. Most of them are usually exist entirely in memory, so it's very, very efficient. So that was search. What happens? What does it mean to make a full text search? So to that concept that I just explained, we add another complexity. Instead of just taking an entire value and putting it inside a table, we do another step, which is called tokenization and an analysis, which is another step on top of that. So, for example, I have these 6 documents right here. And think of them as documents, as values that are going to go into one of those tables that I just showed. So let's, for example, assume this is the title, the title field. So I have 6 sentences, 6 content pieces that are going to go to the title field, and I need to somehow make them full text searchable. That is, I want to be able to find them even if I didn't use the entire string as my search key. I want to be able to find one simple word and to be able to issue a query with one simple word and be able to find all the documents that contains that word. So I'm doing the exact process as before, only I'm adding a tokenization process. That is, I'm going through this sentence here. When I'm indexing the first document, I will break it up on the spaces, for example, or on punctuation marks. I will break it down into individual units, which will be called terms instead of the entire thing as we saw before. Now each word is going to be considered a term. I'm going to repeat that process for the entire 6 sentences, the entire 6 values, documents, and I will put them in this data structure here. It's basically the same one as we had before, but now I'm considering each word as a term and not the entire sentence. So you can see the table is actually alphabetically sorted. That was true before as well. So it is very easy for me to go through the entire table very, very fast. And each word is again going to list all the documents that has this word in them. So whenever I use, that's the same table just enlarged because usually people don't see that. So now whenever the user queries for a certain word, we can just scan the table very, very quickly, find the word. For example, the user who asked for all documents with the word keeper, so I'm going to find that word in that table and be able to know that documents 1, 4, and 6 has that word in them. Now, one thing you should know, that word keeper here is between 2 other words which are quite similar to that, right? I have keep and I have keeps, and I only found keeper. Now, keeper and keeps and keep might have, at least for me, for the context of my data, it might have the same meaning or the same I don't know. I would want to find those words as well when the user searches for keeper, but I didn't. Why? Because the search engine here, when it does its magic, it basically goes and finds the word in its exact form. I had one assumption here that is not highlighted. I did lowercase everything. After I split the words in spaces, I did take the words and make them lowercase. But that's one thing I did. But I didn't do any normalization whatsoever to the actual term here. So if you would want to find keep or you would want to find keeps, you would have to actually perform an explicit query on those terms as well. So this is exactly this topic of term normalization. We are going to discuss this a bit more later, but there is, after I'm breaking sentences, content on spaces, for example, and that's, by the way, again, another assumption. I don't have to split on spaces. I can split on whatever. And again, punctuation marks are usually what I would split on, but I can decide, for example, not to split on the @ sign, so I can preserve email addresses, for example. And this is actually this is something that people actually do. So after I'm deciding what I'm going to split the actual sentence on, I'm going to decide what is going to be the normalization process that I'm going to do, right? So in this case here, I want to decide, I want to normalize those three terms here, keep, keeps, and keeper, to be on the same, to be the same entity, to be the same term. Once I do that, I can allow the user to find more relevant documents for him. So that's one normalization. And another normalization, I can say, okay, I have a lot of terms that are very, very common and they don't contribute anything to search. For example, this is not the practice today, but about 5 years ago, the people would have talked about stop words, right? In English, for example, we have about 10 words which are stop words, basically. Don't contribute anything. The it, is are words that are usually not, that don't mean anything for search or in the content by themselves. So here I color them in gray. You see the, where, head, in, those words, I color them in gray. The practice until about a couple of years ago was to actually remove them in there entirely. Today we have better practices to be able to search on stuff like to be or not to be, right? So all of those words are basically stop words. If I just remove them, I don't allow my users to perform such searches, and my users might want to perform those searches. So this comes in the expense, obviously, of index size, and sometimes in the expense of relevance. The more that I put more terms, I allow for searches to be more relevant. The more terms I remove, I might hit my relevance, etc., etc. So that's a lot of theory. Just to cover some bases, I'm going to show you an example in just a bit. Before an example, because we are coders, we can treat code as an example, right? So here's one. If I wanted to implement what I just showed you in theory in code, this is how it would look like. Can you guys in the end see? Great. So I start with defining a sorted dictionary. That's my highly optimized data structure, right? It's basically a dictionary, and so it's alphabetically sorted. It's not a dictionary in the sense of a hash map. And that dictionary is alphabetically sorted, so it's very, very efficient in looking up terms alphabetically. And once I sort things alphabetically, I can navigate very efficiently through all the terms. So I create that dictionary, and whenever my user wants to index content, I send a list of the documents, and I'm going to iterate through all the documents, and for each document, I'm going to split the actual string on punctuation marks and white spaces, right? Once I did that, I broke down the sentence or the actual content into individual pieces, which I know each piece is a word, right? So now I have a list of words, or as we call them, terms. And then each term, I'm going to normalize before I put it into the dictionary. What do I mean by normalize? That really depends. It depends on the language. It depends on the actual context of your data. Here, what I'm doing is some sort of English stemming, which basically removing an S and an ES. Okay, that's half the work of a normal language stemmer for English. And once I normalize that, I can add it to the dictionary. Now, I'm not just adding it, I'm adding it along with the actual number of the document I found it in. So I can go back, and when I search, I can get a list of all the documents that it appeared on. So that's quite a bit of code, I would say. Whenever I search, I have significantly less code, right? I have I'm searching using a term. I want to get back a list of documents, and all I have to do is look the actual term within my dictionary. Before I do that though, I am going to normalize again, because if I have a normalization scheme, I want to make sure that I'm in line, right? I'm indexing and searching using the same technique. Because if I'm lowercasing, I want to make sure that all queries go lowercase as well. So I'm doing that step of normalization. Once I did that, all I have to do is look up on my fast dictionary. So you can see that indexing is very, very demanding operation. It usually also involves a lot of I/O operations, but search is very, very efficient. And again, I said this again, a lot of times the actual search operation happens entirely in memory, because this is usually what search engines try to do. So all of that is theory, right? We've seen how this actually works. We learned about the actual concepts. Any questions so far? All right. So this would be the naive code of implementing this ourselves. However, we don't need to implement this ourselves, because smart people already did that. So Apache Lucene is a project that is started around the year 2000 and is today, I think it's safe to say, one of the fastest growing projects, and it is highly supported. It's written in Java. It's completely open source using the Apache license, obviously. And there are ports to other languages, Lucene.NET and C-Lucene to C++, which both I'm somewhat involved with. You have to Python, you have bindings to other languages as well. And that's a very mature library. It gives you quite a lot of power, and it actually takes all the heat of performing indexing, performing searches, and making that very, very customizable, very, very flexible, very easy to work with. So we don't have a lot of time. So I'm going to skip this part here. Basically, this code here shows you how to index in Lucene. You'll understand in a second why I'm skipping over that. Basically, you have an index writer, and then that's how you index, and then you have an index searcher. This is how you search. Okay. The reason I skip this is because of ElasticSearch. ElasticSearch, to my opinion, entered the market, I don't know, 2 years ago or something like that. And I think it quite changed the game, because now, for example, what happens when you have an index, a Lucene index, and you index all of your data, and now something happened and your company just grew very big, and your one server cannot handle the load. Either it has too much data it needs to handle, or I don't know, you have too many users and you cannot perform very well with all the requests that you get on that index. How do you deal with that? So ElasticSearch born out of that. It said, I want to be able to distribute a Lucene index, right? So Lucene doesn't come out of the box with that ability. With Lucene, you would have to somehow wrap it and do that all over yourself, because all Lucene does is take a stream of text, index it, allow you to get a query in a certain way, and then search on that index. If you want to be able to support that in a distributed environment, you would have to implement that yourself. If you want to replicate that index, you would have to implement that yourself. That's basically exactly what ElasticSearch does for you. Now, ElasticSearch, not only that it does that, it is able to replicate the index for you. It is able to shard the data for you. For example, if you have a lot of data and you want one index to exist in multiple parts on a lot of servers, ElasticSearch does that for you. It is also able to manage its own cluster of servers. You don't have to do anything. You basically bring one ElasticSearch node up, and then you bring more nodes up, and they just talk to each other and recognize each other. They select their own master, etc., etc. All the distribution work that is, as some of you may know, very, very difficult to do right, it is already done for you. Now, ElasticSearch doesn't end here. It does a lot of other stuff. For example, it is the entire ElasticSearch thing is exposed through the REST API. Okay, so you basically can talk with ElasticSearch using any language of your choice. ElasticSearch also it has a lot of bindings to many languages. So ElasticSearch is written in Java as well, and if you write Java, you would usually prefer to use the ElasticSearch Java client, which is a dedicated client. It talks a bit differently. It doesn't use the REST API. It's more, it's a better option for you to talk over the network. It uses netty and stuff and serializations. But so if you use Java, you probably use the actual ElasticSearch as your client as well. But if you write in .NET, how many are here are .NET developers? Full room, almost. So if you use the .NET, for example, you would go with a library called Nest, which, can you hear me? Which is, it is implemented on top of the REST API. And it does a lot of really nice things using the C#, the features of C#. That's dynamics, that's expression trees, link, a lot of really nice deserialization, deserialization, a lot of really nice things. So use Nest, for example. If you use any other programming language, may it be Ruby, PHP, whatever, you can always use the REST API directly. And again, you would probably have a binding for that already written. So another thing, another important feature of Elasticsearch, it's not only a search engine and a distributed search engine and a REST API for search, it is also very, very easy to extend. So you can actually treat Elasticsearch as some sort of a server you can implement things on. So Elasticsearch has many types of plugins, and each type of plugin is able to answer different needs. For example, you can implement a site within Elasticsearch. You can literally use Elasticsearch as a web server. I don't recommend you to do that, but again, it has a lot of functionality you can actually exploit. And one last thing, we are going to see that in a second, you can use Elasticsearch as a NoSQL database. Okay, it is very, very, it has all the semantics that you actually need to use it as a document database. Again, that's not going to be my first recommendation. Use Elasticsearch as your database, but Elasticsearch has all the semantics needed. And if you already use Elasticsearch for search, you would just as well use it a bit more and use it as a database to store some documents you might need. If let's say like that, if your main concern is search and you have some documents to store, don't look around, just use Elasticsearch. It will be much easier for you. So here's the REST API. Basically, every Elasticsearch node endpoint is going to look like that. You would have the actual server listening on a certain port, okay? So this is the 9200. It's usually the default HTTP port Elasticsearch is listening on. And then you would have two things. You'd have the actual index name, and within each index, you would have a type. So you can store different types of data within one index, and you can have multiple indexes. So the multi-tenancy here of multiple indexes can be used, for example, for different clients, for different applications, etc., etc. And then obviously each document that you put, you can use an ID for, right? So you have that endpoint here, and what you do, you send it a JSON document. Okay, so Elasticsearch works with JSON. Once you put the JSON in, you can retrieve it back, right? So this is a simple GET request saying, please give me the document ID 1 from that index, which is under this type, and you will get it back. And this is how search would look like, right? So you would go again to that same endpoint for that index, for that type. You'd say you want to search, and then you would send your search as a JSON again. Now, sending a search as JSON really gives you a lot of ability. we don't have much time to go through all the search types that Lucene supports, and ElasticSearch supports all of those and adds a few more, quite a bunch more. So you can actually take all those search types that both Lucene and ElasticSearch support and pass them as a JSON object. You can structure them very, very nicely and send that as a search. In this URL, in the actual ElasticSearch guide, you have everything quite well documented. So once you executed a search, you will see the search results quite nicely. You'd have some report on the distributed features of ElasticSearch. I mean, how many shards did you use to query, and how many were successful, how many were failed, and then you can get the failures, how many hits in total, and how many hits you got, because you can page through results. And then you can get the actual document or some fields from that document if you wish. So far, what we've seen until now is how we can make search. Our searches work behind the scenes. Lucene uses the inverted index concept behind the scenes. It is highly optimized, so you have everything, usually everything in memory. And then you have ElasticSearch, which builds on top of that to actually do that in a very easy to understand way, using a very nice DSL and in a distributed manner. So far, so good. Before we go any deeper, are there any questions? Okay, it's either I'm going too fast or I'm very, very understandable. So let's go back a bit. Let's go back to the first example. We've seen that when we have a lot of documents and we index them within the inverted index, we end up having multiple tables. Let's think about them for simplicity's sake as tables. And each table is going to have all the possible values, right? And each value is going to point on all the documents that has this value. Now, when you come to think of it, this is actually quite a lot of data and quite a lot of useful data. We can do a lot of things with it. So, for example, we can do faceted search, or it's also called drill down. Whenever you make a search, you can look at the actual results, and because you have all of that data usually in memory, you can quite efficiently get some perspective on the actual result set. You can look at the results and you can say, okay, so I have 1,000 results, but I know that 900 of them are under one category, and what did I say, 900? So 100 are under another category, and I'm actually interested in that category, not this one, and I'm very, very efficiently drilling down and kicking out 900 results out of 1,000. So you've seen this in a lot of places. You've seen this in LinkedIn, you've seen this in eBay, Amazon. Everyone nowadays does that, and you can get that quite free with using a search engine. And we'll see a live example in just a minute. And you can also do auto-completion, right? I know all the possible values. I know that if you want to look for a specific author, I know all the authors in the system, and they all exist in memory. So I can just look up at that table, and whenever you start typing, I can just complete whatever you're typing based on those values. And again, I'm using very efficient data structures which are alphabetically sorted, so it's practically zero work for me. I can also do autocorrection, right? I can look at those values that I have, I look at what you are typing, and if I don't find anything that matches whatever you're typing to what I know, I can use some algorithms to perform distance matching, edit distance, right? I can try and see whether, if I'm making some amendments to what you're typing, whether I can find something that may be of meaning to you. And I can also use a concept called the bag of words model. That basically means if I have one document and I'm breaking it down to words, I can count how many times each word exists in the document, and by that give a document some sort of a vector, right? And that vector is going to be assembled of all the words within the document, and each word is going to say how many times it appears. Okay, so, and if I can go even further, I can say that I can look at all the documents in my system and give some sort of statistics, how often a word appears in my system in total, or in a language even, right? And use those statistics to give each word a weight. So I'm ending up having a vector which is assembled of all the words within the document, or at least the top ranking ones, so the vector isn't too big. And each word in that vector is going to have a weight, so that is going to influence the direction of the vector. So I can describe a document as a vector and use that vector, which is a mathematical entity, and execute that as a search, right? I can now tell the search engine, give me all such documents that have all those words in that frequency, right? So it might be a bit hard to comprehend, but that functionality actually exists, and it's called more like this in Lucene. And you probably know it from Amazon or eBay, for example. So many algorithms will use hits, right? Will say actually show you real data on whenever you bought a product, and it will actually be able to do some link between this product and products that other people bought. But a lot of times it will lie. It will not do that. It will actually look at the words within the product title or the product description, build up such a vector, and use that vector to search other products. So you don't have to build like massive statistic system to look up whatever other products people bought after they bought this product. It can just do some simple vector search based on words and weights of those words. And there is also something which is very hot nowadays. It's a geospatial search. It's basically being able to take a coordinate on Earth and be able to break it down into squares and regions on the planet, and be able to represent that in a very searchable form. That's a topic for a separate session, but it is also something that search engines can do. And actually, .NET developers, there is a new spatial.NET contribution to Lucene, which actually does that quite nicely. And if any of you guys know RavenDB, this is exactly what RavenDB uses behind the scenes. I mentioned that all of that data exists entirely in memory. So everything happens very, very fast and very, very efficiently, usually. So that's exactly why search engines can be used to live crunching of data. And this actually happens using a project called Kibana. Kibana is 2 weeks ago, I think, it was sort of brought up to be part of the ElasticSearch project. And when using a log stash, it can actually take your logs, break them down into meaningful data pieces, data rows, and ElasticSearch will take them and perform a lot of smarts. Okay, it will be able to perform a lot of what we call faceted search. It will be able to do faceted search on those rows of data, and Kibana is going to show that very, very nicely. Kibana has very nice demo of that. I think it's worth seeing. So here is an example, the official Kibana example. This is what it shows. It basically takes standard Apache weblogs, right, hits on web pages, and it is able to show you graphs like this. For example, this is how many hits I got, and it is able to break it down based on files. So it can tell you that most of the hits asked for HTMLs. The yellow here is PHP, right? The bluish is CSS. We have orange and we have red, and each color represents different data type. So we have this nice graph here. We can see the actual logs here. So what happens here behind the scenes is we have for example, many web servers. Each web server is going to have a log stash shipper. Okay, log stash is a product that it knows how to take logs and break them down. And there is an ElasticSearch plugin that actually lets you push from Logstash, from the output of Logstash, how it crunched the logs into Elasticsearch. And Kibana, this is what you're seeing here, is the web UI that it knows how to query Elasticsearch and ask Elasticsearch to crunch the data and show you that on graphs. So that's a very nice example of how you can take a lot of data and do live analytics with it. And it's actually real-time search. It can update as it goes. So let's see a quick demo of what I just showed you. So this is how Elasticsearch looks like. I'm launching it now. You can see I'm using this version here, and it binds on 2 ports, right? I have this port here, which is the HTTP port, and this port here, which is the UDP port. Basically, this port will be used for other Elasticsearch nodes to communicate with one another. And you can see it says that it recovered 1 index. That's because I already did some work to index something. What I did was to take the entire English Wikipedia, which is a 10 gigabyte download compressed, and index it completely into my small laptop. Let's see how it worked. So before we do that, let's look at the indexing code. So this is where my actual Wikipedia dump was. Here I'm connecting to the actual cluster, or in my case, it was a 1-node cluster. I'm doing some mappings to define how I want full text search to work. This is something that I just wanted to optimize things further. You don't have to do that. And then what I'm doing, I'm building a JSON object here. It's called an X content in the Elasticsearch Java client. But basically, I'm building a JSON document, and that JSON document is going to have a lot of fields. So I'm using in the backend, I'm using a Wikipedia parser that knows how to take the compressed form of Wikipedia. And then I'm parsing, whenever I'm parsing each page, I'm building a JSON document for each page. It will contain the title, the text, some metadata on that page. What's important is to notice this category thing here. Each Wikipedia page can tell you it has a category. Usually a page will have multiple categories. And then I'm pushing it to Elasticsearch in bulks to make this even faster. So this is my Java indexing code. Everything is available on GitHub. I have the link in the end of the slides. So what I did, I built an AngularJS app to query Elasticsearch for data. So I'm going here, and this is my search screen. I can start searching, right? So let's type Kraków, see what I get. This is the first search. It may take a bit or more. Yeah, okay. So screen resolution sucks. So I get how many? 987 results, and you can see that the results are more or less sorted in correct relevance, right? So I get the actual city of Kraków first, and then I get other things that are related to Kraków. So you can see that the first result contains 2 words in the title, right? And I have the word Kraków itself appears several times in the actual content. You may note that this spelling here isn't highlighted. That means that Elasticsearch, or my Lucene basically, didn't recognize this as a match. Any idea why is that? Not lemmatization, normalization basically. Lemmatization is another step. Basically, what I didn't do here is normalize this O, or how do you call that? This U, this U here into a letter, right? So when I search for Krakow with a normal O, I won't find that. If I will search like that, right? This is the Lucene syntax for querying. Notice, see how the number of results changes, right? I just multiply that by, I don't know how many, about 4 times. So this is actually what we talked about, term normalization. So the actual best practice is usually to have that normalization happen in the search engine. I didn't do that on purpose to show you this, but this is usually what you would do. You would need to understand the data that you're indexing, the language, the context, and to be able to put that knowledge to take into place. For example, here, what I was missing is in something that's called an ASCII filter, okay, something that is able to turn those spatial letters into their ASCII equivalent. And here I get the actual Krakow city and not the disambiguation page. Another thing that I might want to show you is that actually I can tell ElasticSearch or Lucene to prefer results in a certain field over the other. So whenever a word I search appears in the title, I would rather show that result instead of the word that I search, it appeared in the actual text. Because if a word appeared in the title, it will probably mean more. Or maybe the page really talks about that actual subject. So ElasticSearch and Lucene also support the notion of boosts. I can boost a certain field, tell Lucene or ElasticSearch it's worth more. Let me just quickly show you the faceting in action. So what I'm doing here, I'm basically performing the exact same search. Let's just use this hack. And, okay, low resolution. Basically, I have the results here, just as before. Sorry, maybe my fault. So I'm looking again for Krakow or Krakow. And I'm getting all the results that I already know of. But this time I have this list here. Now, this happens live. This is not pre-computed. It is being computed on the fly as I make the search very, very fast, as you can see. And what happens here is for all the results that I got, I can tell you that I have 600 results that talk about living people, and 147 results talking about people from Krakow, and I don't know, whatever, Polish historians. So I can break down the results into the actual categories they were taken from. Now, if I click on anything, for example, if I click on Polish poets, you'll suddenly see I drill down into only 60 results. And on those 60 results, I can even drill down further based on other categories that are now relevant to my search, my new search, and so on and so forth. So the actual Wikipedia doesn't have that search ability. And this search is it took me literally a couple of hours to build that and 2 days to index, but who counts? But the main point is it is really, really easy to do. And I will just put the last slide that you'll have the link for that. And if you guys have any questions, I'll be happy to answer. Yeah. A day and a half, yeah. What changing the data? One page changes. So if one page changes, Lucene doesn't know how to delete indexes, how to delete a document within an index. So what you do is, it doesn't know how to update. What you would do, you would go and delete that specific document and re-index it. And ElasticSearch is a very easy to use API exactly for that. Yeah, because you only do one document. You don't have to mess with the entire index, yeah. Yeah. You mean like that? So if I want to find Krakow and poets, okay, the same. Okay, so you use phrase queries. I won't find anything right now, probably, but you do it like that. Okay, so that what I'm using here is the Lucene or ElasticSearch query string. So it is going through some parsing phase on the server. Okay, there are other better ways to do searches with the ElasticSearch, but this is basically the easiest way to do that. So if you want to use to use proximity in your searches, you do something like that. If you want to say, I want these two words to appear within distance of 5, you would do something like that, and hopefully we'll get results. No, we don't. City. It works. Yeah, other questions? Yeah, give me a word. It works. Any other questions, guys? Yeah. What do you mean similarity? In relevance or in the products? Okay, so in my opinion, it's two different beasts. It's a big argument in the search community, but basically, ElasticSearch was built from the ground up to be super scalable and with a very easy to use DSL, and it evolves very, very fast. It just in a couple last weeks, they added tons of new, very useful functionality. Solr is part of the Lucene project. Okay, it is a search server. I mean, it does encapsulate Lucene as Elasticsearch does, but it was rebuilt right now to be more to implement scalability, to implement the distribution features, right, replication and sharding from scratch, because they implemented it they took some design decisions which I think are incorrect, and let me just say this, their DSL is XML. Yeah, other questions? Yeah. So you use stored fields if you are in Lucene. Okay, you can store fields. You can just take the entire text and store it, and Lucene will be able to give it back to you. Elasticsearch does it in a nicer way. It just stores the entire document that you indexed by default. Yeah, I abstracted a lot in this talk. So you would have those tables, and you would have more files that include the actual sources of the, yeah. Yeah. No. Okay, I'm not repeating the question. Sorry about that. The question was if Lucene has the ability to detect languages. No. All Lucene does is index and some search capabilities. If you want to parse, for example, Word documents, PDFs, whatever, you would have to use your own tools. So Apache has a project that does that for you. And language detection, in Bazilla, we use, the Google has some really nice code that does that. But usually language detection has its errors as well. So, yep. Yeah. Yeah, so the question is how does Elasticsearch, right? We're talking about Elasticsearch. How does Elasticsearch handle frequent updates or indexing, right? So very well. Elasticsearch, no, it is scalable. It does a lot of in-memory operations to make this even faster. Whenever you have replicas, right? You index to one server, it knows how to spread the writes or the updates to other servers, it knows to handle failures, and it can operate in high update rate, yeah. Yeah, yeah. It handles all the caching for you, but you still have control over that. It has many caches, many types of caches. You have control over all of that. Yep. Elasticsearch is a competitor of RavenDB, you could say. Elasticsearch is more of a search server, and RavenDB is a database server. So Elasticsearch has document database capabilities, but it is a search server. It has a lot of stuff that you would want to have in a search server. And RavenDB is a document database that has a lot of stuff that you want to see in a document database, but it has full text search capabilities. So completely different products, completely different companies, completely different. Yep. How would you? The question is, how would you measure relevance, basically? Let me ask you this. Whenever Google shows you results, how can you tell that the results are really relevant for your search? Maybe Google hides something for you. Maybe there is something that you don't really, doesn't show up. Because Google failed to index something, because your query wasn't good enough. How do you measure relevance? Relevance is something that is very, very fragile. There are tools to do that. Usually you would measure relevance in a sandbox. You would have a lot of data, you would index it, you would have many, many queries, and you would have people actually rate those documents, certain documents that are expected to turn up for certain queries. And again, all of that in a sandbox. And then you could be able to measure different performances of different search engines. But again, we don't really know what the performance of Google in that respect, for example. Microsoft? You mean OData? You just implement OData on top of Elasticsearch, I guess. It's just an API. Yeah. Yeah. Yeah, you have that. I have that in the last slides on purpose because I knew someone would ask that. So you have this analysis chain. Okay. We have time. I don't know. We good? Okay. 1 minute and a half. So the entire white stuff here is Lucene. This is what Lucene does and basically what Elasticsearch does. Yellow here is the data sources that you provide, and that red stuff here is your responsibility to do, okay? And what happens is you have, in that analysis chain, you would have different analyzers, and each analyzer is going to perform differently, yeah, I know, differently on each type of data that comes in. It will output different tokens. Okay, so thank you very much. I'm here if you want to ask any other questions.